Hello and welcome to this lecture number 3 of week 2 of the course on control engineering. So, so far we have in the previous lecture started off by arguing the difference between time and frequency domain characteristics where a time signal x of t we could compute its value at different time instances. And in the frequency domain characteristic, we saw how many frequency components each of a signal had together with its phase plot. So, what are the advantages of each of these domain, and are there more domains that needs to be investigated? A given function or signal can be converted, of course, between the time and the frequency domain. And what Fourier taught us via the Fourier series and the Fourier transform was that any signal in time domain can be represented as a summation of sinusoids of different frequencies. And why are sinusoids interesting to us? So much of our course will focus on LTI systems. So if I take a LTI system, I give it a sinusoidal input of the form A sine omega t. The output will also be a sinusoid. Only difference will be that maybe it will have a different magnitude. The frequency will be the same. Possibly the signal will be shifted by some phase shift. So the sinusoids are preferred because they do not change their shape when passed through an LTI system. There can only be some kind of amplitude gain or attenuation and a phase shift. The detailed derivation of this we will see during the course. So, and then each domain represents with different kind of information of the same signal. Again, depending really on the objective or analysis, one domain will be advantageous over the other domain. Like signals can have different characteristics with different frequencies. For example, a system can represent a high pass filter, a low pass filter, a band pass filter. These are essentially obvious while we do the frequency domain analysis. Systems could also have components which are only low in frequencies. For example, in the case of control systems, we will see how disturbances are essentially low frequency signals, and noise is largely attributed to high frequency signals. Okay, so in the previous lectures, we also saw the notion of an impulse response. We also had the notion, therefore, of convolution, different test signals which the system can be subject to. So we classified our basic signals as an impulse. We had the unit step, and we saw how closely related both the unit step and the unit impulse are. And we also saw the unit ramp signal. We discussed in detail about the convolution operator with its different properties of time shifting, its properties of commutativity, associativity, and so on and so forth. Let's look a little more in the domain that we are familiar with, that is starting from the domain of electrical circuits. So I start with a circuit which has no source, right? So there is no voltage or current source. All I'm interested here is there is some initial flux or initial energy or initial current in the inductor when I start this circuit. How do I write down the dynamics of the equation? I say just use Kirchhoff's laws, Ri plus LdI by dt equal to 0 or something like this. Okay, so if I in this representation, if I of 0 equal to 0, I of t will also be equal to 0 for all time t greater than or equal to 0. There will be nothing that the inductor can offer to this circuit. And there is no external voltage source also. Just like a pendulum starting from here will just remain here. If it starts from some other non-zero position, it might just keep oscillating until it comes back to its equilibrium or original configuration. Okay, so I can rewrite these expressions. I can say I do di by I is negative of r over L dt. I integrate both sides, very basic notion of integration. And I get the solution to these equations of this form, that I of t is I0 e power minus RT by L. Okay, how do I actually know that 2 is a solution to 1? One thing is we check, substitute 2 into 1 and check whether 2 satisfies 1 and also the initial conditions. So before we look at the response, let's work out this. So this is my equation and this is my solution. So first is check for initial conditions. Initial conditions means what happens when t equal to 0. This will give me I of 0 is I naught e power minus r over L times 0. E power 0 is 1. So I have I of 0 equal to I0. So the initial condition is now satisfied. Okay, now check what happens if I substitute this back into this, which essentially means I should get something like L di by dt is negative of r times I. Okay, so what is di by dt? Di by dt is I naught negative r over L, negative r over L e power minus r over L t. All this is multiplied by L. So on the left hand side, I am left with minus r e minus r. There is an I naught e power minus r over Lt. Look at what this is. This is exactly my I of t. So this is minus r times I. Right? So this is LDI by dt is negative Ri, which also means the same thing, right? So one, the solution satisfies initial conditions, and two, the solution I of t also satisfies the original differential equation, that is Ri plus L di over dt equal to 0. Okay, so going back here, starting from an initial condition, how will the circuit now behave? At t equal to 0, I started I naught. Let's assume that I naught equal to 1 for simulation purposes. And how does it decay? Well, it doesn't, all entire current doesn't come to 0. So what happens in this circuit is that the energy that is stored in the inductor initially is now slowly dissipated across or via the resistor, and eventually all the energy is dissipated and it will go to 0. Okay, so this is I can also look at it mathematically. What does this mean mathematically? What is the limit of t going to infinity I of t? This is simply limit t going to infinity I naught e power minus rt by L, and we know that limit t going to infinity e power minus r over Lt goes to 0. Okay, this also explains the dynamic behavior of this, right? So we called in our earlier lectures, we called something like the transient and the steady state, right? We had seen how a fan, for example, if I switch it on, it takes some time to build up its speed. If I switch off a fan from initial speed, it doesn't come down to 0 immediately. It takes some time to go to the 0 speed. This is a little mathematical explanation to what you're seeing here, right? So two things we have seen here. One is, how do I mathematically represent a response of a source-free RL circuit? And how does it even respond to, how does it even correspond to the system classifications we had earlier done? This comes under the classification of dynamic systems, systems which have memory. This is the memory part of it. It remembers some initial condition, and because of the dissipation across R, all the energy gets dissipated. Okay, what happens now when I have a voltage source? Let's see, there is some V here of say some value 1. Okay, so my equations now change slightly here. So I'm also assuming for simplicity that the initial current is 0. And now I will see how the current might build up across the circuit. Will the current, if I just say V for a resistive circuit, V equal to IR, when V equal to 1, I immediately equal to 1 when R is equal to 1. When V will be equal to 2, I will immediately be equal to 2 for R equal to 2. What happens in an RL circuit, and how do we explain that behavior? Okay, so I look at, so my equation now will have the voltage source, Ri plus LdI by dt is V naught, or alternatively written in this form. I'll skip how we do the solutions of this, but this will lead to an expression of the current as I of t is V naught over R 1 minus e power RT by L. Okay, again, does it satisfy the equation? We'll just look at the initial conditions, right? What happens to I at 0? I at 0 is V naught over R. Inside the bracket, I have 1. And e power minus RT by L. So this will be 1 when t equal to 0. So the initial condition is 0. This is the initial condition. Okay, now what happens in the steady state as t goes to infinity? As t goes to infinity, this term goes to 0, and I've just left with V naught over R. Okay, again, in this case, these are my transients, and this is the steady state. Just like my fan builds up the speed, and once it reaches its full speed, it just stays there. So if I just look at a fan, this is just the full speed of that particular regulator position. Okay, two things that is common is we have terms here which are some kind of exponential term here, and also an exponential term here with RLs. Similar behavior can also be seen when you just have, say, R and C circuits. Okay, nothing changes. Maybe just nothing changes. When I say nothing changes, it means that the nature of differential equations will still be the same. You just write down the circuit laws at this node and so on. Okay, let's see now if I add one more component here. I have a R, I have a L and a C, and I write down my voltage loss at this node. Okay, so for simplicity, let me assume that there is some non-zero initial condition. Right? If again everything is at 0, my system keeps no just is at 0 all the time. Okay, let's say there is some initial current through the in the circuit, and also that there is no that the voltage V of 0 is equal to 0. Okay, so I can write down the equations now of this form. And this is again, I'm just writing down the current loss at that node. Okay, now how does the dynamic behavior evolve? In the first case, we just saw that the system starts from a non-zero initial condition and it eventually goes to 0. If you remember the example of the pendulum that we had, of a simple pendulum, we had an undamped case where there was no damping. For any initial condition, the system just keeps oscillating. We had the response for an overdamped case. So look at this. For example, here I have a non-zero position, a zero angular velocity. Again, I can look at in the circuit also, right? I had a non-zero current and a zero voltage. And what happens is eventually the position slowly comes back to 0, and so does the velocity. In the underdamped case, I start from a non-zero position. It just oscillates for a while before it comes back to 0. Okay, so similarly, we will see in case of a circuit of how do we mathematically look at now this overdamped and underdamped behavior. So solutions to this differential equations are of this form. Again, I'll not go into the details at the moment of how we are computing this, but solution will be again a combination of two exponential terms, where this is called an overdamped case. Critically damped, this both should be same. So I have critically damped would mean when L and C would be satisfying something like this. And lastly, the interesting case would be that of the underdamped case. Okay, in the underdamped case, where mathematically it means something like this, I will have a solution which now has an exponential term, and a sinusoidal term. Okay, so the voltage now has exponential and sinusoidal terms. The exponential term is due to the damping, which is in this case the resistance, whereas the sinusoidal term is due to the interconnection between the inductor and the capacitor. So let's just look at it like this. Right? So suppose I just have L and a C element. This is also called the harmonic oscillator. Okay, so when there is no R element, it's just so the voltage might just have a sinusoidal behavior. Okay, that is what is this, right? When there is no R, there's only L and C elements. It just oscillates. I add a resistance in parallel, things will change. Something else will add up. So this is exactly captured by this R element. So now I have exponentially decaying term multiplied with this with a sinusoid. And what we see is now is that there I will still see some oscillations, but which are decaying with time. Okay, and the response eventually like goes to zero. So now I'm looking at a system behavior or system dynamics, or I can understand the system's behavior via a set of differential equations. In this, I have a first order differential equation when I just had a L and a R, and I have a second order differential equations. Now, when I have a R, L, and a C, I also had a second order differential equation when I was just looking at the example of a simple pendulum. Okay, this is nice. So everything is now captured by some exponential term and a sinusoidal term. Is there something that I can exploit this property and make my solving of problems make my solutions to problems simpler, right? So what did we observe so far is that the solutions to LTI systems, again, all these are differential equations, linear time invariant systems. They're either exponents or sinusoids or combinations of both. Okay, and in frequency domain transformation, signals are decomposed into sinusoids with some amplitude and some phase at each frequency. And to account for the idea of exponential response, we extend the idea of the frequency response. I'm not just looking at some signal as combination of sinusoids, but combination of sinusoids and also exponent terms. And therefore, we define a new transformation such that signals are decomposed not just into sinusoids, but also into sinusoids and exponents. So this is where the notion of Laplace transform comes in. The Laplace transform decomposes signals in the time domain into a domain of both sine and the exponential function. Okay, so the domain of this is called is called the S domain, named after Simon Laplace. In this case, S is a complex number, right? The S plane is a two-dimensional one. One is described by the frequency omega, and second is described by the exponential term. If that's largely captured here, right? So if I again go back to see, I have in this a sigma from the exponential term and omega from the sinusoidal term. Okay, so now I call this S as my sigma plus j omega, and given an S, we can now get e power st. I can write this is as e power sigma plus j omega t, which can be expanded to what we see here. At e power j omega t is cos omega t plus j sin omega t. Here, j is denotes the square root of -1. Okay, this is the essence now. Why am I doing this? Now I am having a transform that will decompose signals in the time domain into a domain which domain of both sinusoidal and exponential functions. And this will help me solve a lot of problems throughout this course, as we will see. Okay, what's the definition of this Laplace transform now? So given a signal xt, Laplace transform is now defined by this by this integral expression here. Okay, this L is the Laplace transform operator, and existence of this, again, you see, I'm integrating some quantity between 0 and infinity, which means that this integral should converge. So existence of this Laplace transform depends on the convergence of this integral in this equation 1, which again depends on the value of sigma, right? We'll see slowly with the help of some examples. And the region in the S-plane in which the Laplace transform exists for a function is called the region of convergence. Okay, if you are not understanding much, all we have to see is that this value is finite, or it just does not kind of blow up, because integral is essentially the area under a curve, and that area should be well defined. Okay, so we will learn this by looking at some very basic signals. Okay, some of them I'll do the derivations, other I'll just leave as an exercise. So the basic test signals that we saw the impulse, we saw the step, we saw the ramp, and so on. Okay, so I have an impulse function. So the Laplace of an impulse turns out to be 1. Okay, this is again, I will not do the derivation of this. This is just simply integrating 0 to infinity e power minus st dt and exploiting the fact that sigma t only occurs at t equal to 0. Okay, so the Laplace transform of e power minus at. Well, I just go to the definition. What is the definition? Is e power, the definition of Laplace is you take the function, sorry. Okay, somehow my machine just wants to go to the concluding slide. Will not let it go there as quickly. Okay, so the definition is 0 to infinity, the function e power minus st dt. Okay, so 0 to infinity, the function here, and e power minus st dt. Okay, I do all of these things here, and I will see. Okay, so just write this a little carefully as e power minus s plus a times t over minus s plus a. Now I'm evaluating these integrals at 0 and or these expressions at 0 and infinity. At 0, okay, so what must happen here is that if s plus a is greater than 0, then at infinity this goes to 0, right? So if s plus a is greater than 0, so then e power minus s plus a times t, the limit of this as t goes to infinity, this will go to 0. Okay, and I'm just left with the value now at t equal to 0. That beautifully comes up to be this value. Okay, so this value at infinity will go to 0 only under this condition, that sigma must be greater than the negative of a. And this is also largely related to the region of convergence, or that region in which this particular integral is defined. Okay, so if I just look at, as I said, it's like a two-dimensional plane here. Here, the sigma S plane is a two-dimensional one representing the frequency and other representing the omega. So we largely look at this as sigma, this as omega, and what we want is that sigma must be greater than the negative of a. If this is the negative of a. So this entire region will be my region of convergence where the integral is defined. Okay, the next is, okay, this computation is easy. Just this example actually explicitly shows us the importance of the region of convergence. So, okay, next is the Laplace transform of x of t equal to t, a ramp signal. Okay, so okay, we can also see here is that a special case of okay, we'll just write this down here. A special case when a equal to 0, x of t is 1, that is a unit step, in which case the Laplace transform of u of t is 1 over s. Okay, that's a special case. Okay, because e power a t for a equal to 0, it will just become 1. So the Laplace transform of a unit step is 1 over s. Impulse is just 1. We'll see what it is for a ramp signal. Okay, I have a function x of t equal to t, and I want to compute the Laplace of this x of t, which is equal to t. Okay, by definition, x of s in this case would be 0 to infinity t e power minus st dt. I'll use the standard formula of integration by parts, which essentially means that if I have, say, limits from a to b, u dv is uv from a to b minus integral a to b v du. Okay, so I'll call my u as t. V here becomes minus 1 over s e power minus st. So I'm looking now at integrating these two by using the integration by parts formula. My first term becomes minus t over s e power minus st from 0 to infinity. Okay, this kind of nicely goes to 0, and then I have negative of 0 to infinity v, that is minus 1 over s e power minus st, du is just 1, and dt. Okay, so this is now simple to compute. So what we will be left now is 1 over x square. Now that the Laplace transform of L of xt when x of t equal to t is simply 1 over s square. Okay, nice. So this is nice. So I have Laplace transform of Laplace transform of t is 1 over s square. Okay, we get rid of all these things and just nicely summarize what is going on here. So in general, now if I have the Laplace transform of t of a signal t power n, Laplace transform of t of n will be n factorial over s power n plus 1. Again, this is similar derivation to what we had done for x of t equal to t. Okay, now the next would be what happens to a sinusoid. The Laplace transform of x of t when x of t is a sin xt. So here I will use the property. Again, I will not really derive this, but sine of x can be written as a combination of exponents. That should be e power jx minus e power minus jx over 2. Again, j here is the square root of the negative of 1. Okay, the steps are all written here of how I do the integration. So the sum or to the conclusion would be that the Laplace transform of sine of at would just be a over s square plus a square. We use this property to derive. Okay, and similarly, Laplace transform of cos of at will now turn out to be s over s square plus a square. Again, we'll not really worry about how the derivation comes. The derivation comes from here, and writing down sinusoids, sine of x or cos of x as exponents. Okay, but we'll remember this. Okay, and we'll remember this and use this appropriately in our context. Okay, so now this is fine. Again, I really do not want to spend time on integrating all of this stuff. All I saw in convolution was it was a difficult integral, xt ut minus tau d tau going from 0 to infinity, and I don't like integrals, right? Because there is a very good chance that I might miss out on a minus sign while integrating e power minus s or e power minus t and so on. Okay, so finding xt from basic definitions for all kind of signals is cumbersome in many ways. To simplify, we'll just work around some very basic signals like e power at. We had the Laplace transform of so some basic signals that we derived starting from e power starting from the impulse, starting from e power at, starting from x of t equal to t. Same thing also you can do for here for t equal to 1, right? Which will also give you the uh, what you call this will also give you uh, the Laplace transform for a unit step, not just by looking at s plus a here. So if I just put t equal to 1, which is t power Laplace transform of t power 0 is 0 factorial s times 1. Factorial of 0 is 1 over s. Okay, quick check, some kind of a teaser. Y is factorial of 0 equal to 1. Somebody remembers, we can discuss this in one of those live sessions, either when I am there or when the instructors are. Okay, let's compute what is the Laplace transform of a derivative of a signal x. Starting from the definition, what is L Laplace transform of a signal x of t is integral 0 to infinity x of t e power minus st dt. Okay, what happens when I have dx by dt instead of just x of t? So this will by definition be 0 to infinity. X of t is dx by dt e power minus st dt. I will rewrite this reorganized terms, have e power minus st dx by dt times dt. So I'll call this, again, I'll do integration by parts. I'll call this u, I'll call this dv. So this will be again uv from 0 to infinity minus integral 0 to infinity v du. Okay, so uv will be e power minus st x of t 0 to infinity minus 0 to infinity. V is now x of t. D of u is minus s e power minus st dt. Okay, so again, I look at this term where I have now limit t going to infinity e power minus st. Okay, and because we are operating in the region of convergence, this signal will go to 0. So what will be left here is x of 0 with a negative sign. This is evaluating this term reduces to this, and here I have now, okay, these two negatives become a plus. I have a 0 to infinity x t e power minus st dt with the s coming outside. Okay, so this is nice. So this is just s times x of s minus x of 0. Okay, so let's go back and check what we have written here. Laplace transform of dx over dt is s times xs minus x of 0. Okay, I can then go for higher derivatives. Second derivative will have a s square term and some terms depending on the initial conditions, not just the initial conditions on x, but the initial condition on its first derivatives also. And so on, I can go on till this nth derivative. Similarly, differentiation leads to an multiplication by s. Integration leads to a division by s. Okay, And then I have frequency differentiation. So I have Laplace transform. So I know what is for xt. If I multiply this signal with a t of xt just gives me negative of d over dx of xs. And then I can all the way go on to frequency differentiation by looking at the Laplace transform of t over n xt, resulting in this expression here. Again, I'll not do the details of this. We'll remember this as properties and use them as and when we would need them. Similarly, frequency integration, start from a signal x of t, do 1 over t, and what you get here is a signal of this form. Okay, frequency shifting e power s naught t xt will just go, so the domain will just shift from x, x of s will just shift from x of s to x of s minus s0. Similarly, for a periodic function, Laplace transform of a piecewise periodic function with period p is just given by this expression. Again, I will not do much of the derivations of this, but we will use them when we need and try to also interpret them during that time. Okay, two very initial, two very important properties. So if I go back here to my to this behavior here, right? So I started off with LC circuit without any sources. The current value settled down to a value of 0. Similarly, here I had the RL circuit with a voltage source. The current settled down to a value of 1. Similarly, here the voltage just goes to 0. Even in this case, the voltage goes to 0. So all these are kind of steady state values, or the final values also, as we call them. Okay, so what are the two nice results that we will interpret from here? Okay, so first is the initial value theorem. Okay, I'll just abbreviate this as the IVT. And again, we are working within the domain of LTI systems. For an LTI system, the initial value theorem provides a way to determine the initial value of a time function directly from its Laplace transform without needing to perform the inverse transform. So I start with a time domain, I go to the S domain, I can do all my analysis here itself. Okay, so there is a nice relation that we will see. So mathematically, again, I'll not do the derivation of this, but this turns out to be pretty neat. Limit t going to 0, x of t will just be limit s going to infinity s x of s. Okay, so a little example I can do, say x of t is 3 plus 4 cos t, the limit t going to 0, x of t will be just 7. Okay, I can compute this in the time domain. In the S domain, okay, I have 3 and I have 3 plus 4 cos t. So the Laplace transform of this will be the Laplace transform of 3 plus the Laplace transform of 4 times cos t. Look at the first property of Laplace transform that we are using. That is the linearity. ax1t plus bx2t is just ax1x plus bx2s. Okay, so here this a is equal to 3, a equal to 3, x1 is just 1 or the unit step, b equal to 4, and x2 is cos t. Okay, so this is nice. So this will be 3 times Laplace transform of the unit step is 1 over s plus 4 times Laplace transform of the cos of t. That will be s over s square plus 1. We had derived this property of what is the Laplace transform for a cosine signal. Just here, this one. Okay, so I'm just using these two and get a nice expression of x of s is something like this. Okay, so what is the I'll just compute this expression. Limit s going to infinity, s times x of s will simply be, again, so this s and s will go away here. Here I will have s 4 s square over 1 plus s square, and the limit of this as s goes to infinity, this will go to 4. Again, you can just use some tricks here of dividing by s square and so on. So the value turns out to be 7. Okay, but I said I'm interested in the final value. What really happens to a signal as t goes to infinity? For the For an LTI system, the final value theorem, it should be FVT, provides a way to determine the steady state or the long-term value of an output. This could just be not just an output, but also the error. We had seen how in some of those examples, error was 0.1 because the steady state was going to 0.9 instead of going to 1. Mathematically, this means that limit t going to infinity, x of t is simply limit s going to 0, s times x of s. Okay, let's do this, verify this with the help of a signal. Okay, so I have x of t is 1 minus e power minus 2t over 2. So I'm just looking at this as a limit t going to infinity. As t goes to infinity, this guy goes to 0. I'm just left with 1 over 2. In the S domain, I just again compute the Laplace transforms of each of these, again using the same linearity property. And now the Laplace transform of e power minus at, which was 1 over s uh, plus a. So I have 1 over s minus 1 over s minus 2. I just do this little computation, and I end up at the same value of 1 over 2. And this we will see very quickly how these are much nicer to compute than going to the time domain and so on. Okay, so we'll conclude this lecture here. What we saw in the beginning of this lecture was the solutions of differential equations. They evolved naturally as some kind of combinations of exponential and sinusoidal terms. And a transform we learned which will handle both of these together was the concept of Laplace transform. In the next lecture, we will see the concept of inverse Laplace transforms and then how these are beautifully used to solve ordinary differential equations in a much neater way than we would have learned earlier. That's coming up in the next lecture. Thanks for listening.